It is my pleasure and honor to introduce to you Stéphane Moreau. Stéphane Moreau is our speaker this year. He has had a distinguished career in both academia and industry, and as you will find out later on, this is something that I will harp on a little bit in this forum, how important it is to me to have a good connection between industry and academia. So here's a living example. Stéphane Moreau got his master's degree at Superaero in Toulouse in 1988. He subsequently got his PhD degree at Stanford University in 1993 with a major in mechanical engineering, a minor in aeronautical engineering. And after a few stints in some small companies, he then joined Valeo. And Valeo is a tier 1 automotive supplier to many of the European car manufacturers, a very important part of the European car industry. And but as those of you who have worked with the automotive industry know, it's a high pressure place. So technical development there is not done in the relative calm of the corporate laboratories of some of the big companies, but it's under intense competitive pressure. So it is in this environment that Stéphane worked for 13 years, and then subsequently he took a step back into academia and became a professor at Sherbrooke in, I have to look this up, 2009 as an associate professor. Sherbrooke is a university in Quebec, which prior to his going there, the world didn't know, but now they will know more about Sherbrooke. He has become a full professor there in 2011. He focuses his work mostly on different versions of highly resolved CFT, as he will present to us today. But he also has a strong background in analytical methods for acoustics. And his contribution to this conference is, in my opinion, twofold. It is a little bit interdisciplinary in that I think he will bring out how acoustics interact with other phenomena. And the second aspect of his scholar lecture is sure to be how highly resolved computational methods are advancing our understanding of pertinent physical phenomena in turbomachinery. And with that, I would like to hand over to Stéphane for his presentation.
So, first, thank you all for this very nice introduction, and thank you everybody for actually hosting me today. And before starting actually the lecture, I want to indeed emphasize that it's a very important problem nowadays for most turbomachinery or any rotating machine actually, because there are, I think, more and more noise issues, either in your daily life or like in airports, for example, for aircraft, where we have, I think, more and more issues in big cities. So this is a very relevant societal problem, as Reza mentioned earlier on. It's also interdisciplinary, as Jörg said, because it will basically bring a bridge between classical aerodynamics or unsteady aerodynamics and another field, which is acoustics, okay? And it's a combination of both, and I will basically try to show you that. I also want to thank, this is actually the contribution of many students, so I want to thank all of them, and also the sponsors, and I would say most of this work was also supported by 2 industrial chairs, one in Canada and one in France, actually in collaboration with École Centrale de Lyon, where I had the joint appointment. So I want to thank actually all the sponsors on that. And also for the computational part, you need to have high power computing. So I want to acknowledge also Compute Canada and Calcul Québec that made actually most of this computation possible. So before that, so now we can basically dwell into the problem. The background for turbomachinery noise is twofold, and I would basically split turbomachinery into two fields. One is like the low-speed machines, the ventilation systems, and then the propulsion system on the other hand, so the high-speed machines. And I would say that the differences between the two are both at the design stage for ventilation systems. So as Jörg mentioned, I've been in this business for 15 years, actually. You usually deal with a fan alone or like at most, I would say, a rotor stator stage. These machines are low Mach number usually. You can have like a high Mach number, but their high Mach number is probably 0.3, 0.4, not more. And then low Reynolds number for sure, which means that you have always something like a transitional problem. So you're always in the gray zone, which make it quite difficult. And then because these are machines that are meant for providing airflow, mostly the pressure rise is low. And because of that, you don't need that many blades basically to achieve it. So you have a low number of blades and low solidity. Now, as I mentioned, these machines are under more and more stringent regulations. So there is a high pressure to reduce the noise of these machines. And I'm giving examples here. These are all aircraft examples. This is a typical HVAC system that you have in an airplane, what provides you basically the airflow, like the nice environment in the cockpit. And then, but you have other machines, other ventilation systems, for the cargo, to pressurize the cargo, or also for cooling down, like the braking systems. These machines, I won't really spend much time on it. I gave actually a keynote a couple of years ago on that, so if you're interested, you could see basically what is the status on this machine, on the noise on these machines in this link. And I will mostly spend time on the propulsion system, so the high-speed machines. There you can have a rotor stator, or you can have a rotor stage, or stages. So you can have several stages. And then all of them, they have high Mach number and high Reynolds number. So that makes the problem also a little bit more difficult and more computationally intense. Now, the other thing also, which is relevant both for aerodynamics and acoustics, is you have also a lot of blades, usually. You need, to achieve the pressure ratio, you need a high solidity, and this will introduce actually cascade effects, both on the aerodynamics and the acoustics, and the effects are quite different, actually. Now, for propulsion system, this is very relevant even nowadays, because this is the dominant noise source at approach, and it is also the dominant source in the forward arc in almost like all flight conditions. And we'll see that it's actually becoming even more relevant with the evolution of the propulsion system. And this is actually my next slide to show you some of the evolution of these propulsion systems. And we will start with actually a plot that Chris Hughes did in 2008 at a NASA lecture, where he showed basically the evolution of the propulsion system in terms of two criteria. One was improve fuel burn, which is always what we are looking for, but also in terms of noise. And here it was showing basically the margin to stage 4, which is the current regulation. And you could see that we had actually two different groups. We had the group of the open rotors and contra-rotating open rotors, which were very good at fuel burn. They were providing basically a 25% improvement compared to the current propulsion system, but they were noisy. Okay, they were meeting actually stage 4, but barely. And actually, if we want to move to stage 5, they were not meeting it. So we needed to do something. On the other hand, the turbo engines, so the ducted turbofans, were very good actually in terms of noise. They could provide a significant gap compared to stage 4 and even stage 5. And this was including like high bypass ratio and also the gear fan that Pratt & Whitney has developed. And the question was, basically at the time, if we go to higher bypass ratio, can we actually bring these guys down to basically a better noise reduction? And also on this one, could we also improve the noise to basically reduce the noise from the open contra-rotating open rotors? And basically, what we have seen in the last 10 years is a convergence of these two, actually, towards where my question mark is here. But in terms of integration, because that's not the only thing, aerodynamics and noise, for the moment, the choice has been to go for ultra-high bypass ratio first, and then maybe contra-rotating open rotors in the future. But for the moment, I would say this is like on the ice, so not selected for the moment as the next step. So basically, I would say two propulsion systems we're forcing in the near future, contra-rotating open rotors and ultra-high bypass ratio ones, and the ultra-high bypass ratio are going to be the next generation of propulsion system. But in both cases, you see that the issue was actually to get always improved noise. And both systems have their own tonal and broadband noise. And I'm showing actually an example here of a high bypass ratio, current high bypass ratio typical spectrum, where you see this is the noise level in dB as a function of frequency. And you could see that many components within the turbofans are contributing. At low frequency, it's the jet and the combustion that are competing. And then at a mid and high frequency, it's the fan, the turbine that are mostly contributing. So all these elements are relevant. And what's going to happen with the ultra-high bypass ratio? The jet noise is going to go down because the exit jet velocity is going to go down again. Combustion might actually go up, and for a simple reason, this is not related actually to noise directly, but we want to go to lean combustion in terms of reduction of emission, and this is more unstable. And also because of the increase of the nacelles, you need to make it shorter, so you need to reduce also the number of stages, and now the turbine is not actually filtering as much as it used to, and the combustion noise may actually go out more. So this should probably go up. And then all the other contribution, and mostly the fan, because it's increasing, that's going to actually go up. So this is, I think, the trend we're going to see. So you see that it's already a significant part of the noise, this turbomachinery noise, but it's going to become the major one in all flight conditions. So basically, we need to really focus on this subject. Now, how do we do that? So that's my next slide. These are, so it's a little bit crowded, but I will walk you through it. So these are the different methods for turbomachinery noise prediction, and I will start from the left. Basically, in any turbomachinery noise prediction, you have 3 steps. You start on the left by defining the excitation, and this excitation will come from different noise mechanisms that you will see later. But it could be also, depending on the mechanism at stake, if it's a generation of noise or propagation, it could be a vorticity wave, or it could be an acoustic wave. So you could have an acoustic wave, actually, a vorticity wave. And this could be 2 different excitations, for example. And then you have to define basically how the blade responds to this excitation. And this is my second step in red here. And once this blade has responded, so you have an unsteady loading, this will be an equivalent dipole that you can then consider as propagating to the far field, and you can use some kind of propagator here, either linearized Euler propagator, for example, or an acoustic analogy. And in the examples I'm going to show, it's mostly acoustic analogies. Now, in terms of how to model these 3 steps, you have basically 3 different ways with more and more computational involvement, more and more computational cost. So I'm basically following the hierarchy that Meng Wang proposed in the annual review of fluid mechanics in 2006, where basically you can start by doing everything analytical. And I will show you some examples where you can basically model the whole path here analytically. And then the second, more involved way is basically, but you need there to do a lot of simplification, both on the noise mechanism, the geometry, and also the propagation. Now, if you want to be a little bit more accurate and account for the geometry in a more detailed fashion, you can use a hybrid approach. And basically what you would do is like the first 2 steps will be done accurately with some unsteady computation. And then you propagate to the far field with an analogy. So this is the second step. And then the final one is where you do everything at the same time. Okay, you simulate the excitation, you simulate the blade response, and you also simulate the propagation. This is really the holy grail. But actually, at this stage, it's still very computationally intense. But I will show already some examples of it. And there's one method actually that is helping us actually getting there. Okay, so let's start by the bottom one, okay? Let's start by the analytical approach. What do we need to do, basically, to model each of the steps analytically? I mentioned one thing here also. I include in there also the possibility to connect that with some URANS simulation that are used commonly in design. So this fits here, because basically the URANS will provide you some inputs for the analytical model. But they don't provide, and insist on that, everything which is acoustic is unsteady. So the URANS is not going to give you any noise information directly. Okay, so if we want to do an analytical model, as I said, we need to simplify almost every single step. So the first thing that you do, and I will focus on my turbofan, so the first thing that you do is you assume that the nacelle can be assimilated to an infinite annular duct. So this is the first, I think, assumption. And then the blade geometry that is sketched here is actually described by a stack of strips. So you basically cut your blade into strips. And then on each strip, you assume a simplified geometry, typically a flat plate, and on which you have a uniform flow. And most of the time, you assume uniform axial flow. And then at the final step, you can use an acoustic analogy. And the power of the acoustic analogy is basically to provide you the far-field acoustic pressure simply as an integral form. In the most simplified case, for example, when you have some subsonic flow, you can basically assume that among the three main sources, you can basically neglect the quadrupolar term, the monopolar term, and keep only the dipolar term. So this is one assumption. The other thing, too, is you usually neglect the viscous forces. You see that basically they are not actually contributing to the noise generation. And then if you do that, you have two main assumptions also, that the sources are generated by the flow only, and that you don't have any feedback between the acoustic field and the aerodynamic flow field. Now, the final thing, if you really want to be fully analytic, is if you look at the expression here, if you want to be analytical, you need to have an analytical form of the Green's function. So you need to use a Green's function tailored to the problem that has an analytical form. So this is the last constraint basically on that. Now, if we keep only the dipolar term, you see that basically what is left to determine now from my simplification is really this Fi, so the unsteady force on the blade. And this is the final step that we need to do. So the acoustic, to determine the acoustic sources, the pressure fluctuation on the blade. So now, how do we do that? And you can still do it analytically, again, provided some assumptions. As I mentioned, we use most of the time a strip theory, except in the mode matching that I will talk about a little bit later. So you unwrap basically the stage at a given radius. So this is my green line here. And you end up with basically a cascade, flat plate cascade, as you see on this side. And if the solidity is really low, you can basically neglect the effect of one blade on the other, and you are basically left with getting the isolated airfoil response. So this is what you have to do basically at each radius. Now the next step, and which is valid for most of the components, except I would say the turbine, is to assume that these blades are thin, and that they have that the camber is also not too high, and you end up basically with simplifying with a flat plate. So a flat plate with our thickness and camber. Then, as I mentioned, we neglect the viscous effects. So basically, we are left with obtaining basically the inviscid flow parallel to a flat plate. And to account for the wakes, because this is a realistic feature in all this turbomachinery, we basically have to apply a Kuta condition at the trailing edge. Now, the method, the analytical method for both cases, so if we start with the low solidity, so the isolated profile can be done in two ways. Either you determine the unsteady lift using some Schwarzschild theorem, which comes from electromagnetism, or you can use the Wiener-Hopf theory. So either one are fine. And there is a summary, actually, of all these methods, especially the Schwarzschild one, in a paper that we wrote with Michel Roger in the International Journal of Aeroacoustics. This is for the isolated case. Now, when you have isolated, as I mentioned, we need to account for cascade. And if we do so, we basically get the unsteady lift using the Wiener-Hopf theory. But the only case that is really tractable is when you have a 3D rectilinear cascade. So we basically put the cascade now rectilinear. So this is what you basically have to do if you want to go analytical. Now, what I need to now do is basically characterize my excitation here. What are my possible vorticity waves here, or acoustic waves? So these are the noise sources, and I'm giving the example of a classical ultra-high bypass ratio turbo engine. These are all the sources that you can have. So if I start from the inlet, you might have some upstream distortion coming basically from the fact that you have an angle of attack, or if you have some side wind, this will create an upstream mean distortion. By the way, in green is all the mean effects, so the mean flow effects, and in blue is all the turbulent chaotic effects. And on top of this, or on top of this mean distortion, I might have actually some upstream turbulence also that will basically come an impact or an impinge on the rotor blades. And that will create basically a dipolar source on the rotor blade. Now, on the nacelle, you will have growing turbulent boundary layers, same thing on the spinner. And these boundary layers will impinge also on the rotor. And that's, again, another noise source on the rotor. Then from the rotor, you will have basically growing boundary layers on the rotor blades. And this will create actually the boundary layer turbulent contribution, or actually the self-noise, or the trailing edge noise of the rotor. And at the tip, you have also a gap, and because of that, as everybody knows, I think here, is that you have tip vortices forming, and these tip vortices will have also a contribution to tip noise. So this is my source here. Then this rotor will shed some wakes, and these wakes will impact basically on the outlet guiding vanes. And this impact is actually the dominant effect, both from a mean flow point of view, but also from a turbulent wake point of view. So this is the dominant one in the current architectures. And then you have also some effects. If the distance is close between the rotor and the stator, you might have some potential effect, and that comes from here. I'm just showing the stator potential effect, but you can have also a rotor, actually, potential effect. So you see that overall we have many aerodynamic interactions, and we need basically to do all the steps that I showed before for all of them. Okay, and this has been actually the work that has been done in the past 20 years. One thing I want to emphasize also, when you start having heterogeneous stator vanes and cascade effects, you have an additional thing to account for, but this is feasible also in all these analytical models. So we have several, in conclusions, keep in mind we have several tonal and broadband noise sources. So now to illustrate my word, I will go through two basic comparisons throughout the talk today. One will be the NASA ANCF. Actually, I shouldn't call it anymore NASA, but the ANCF test case that was originally at NASA and that is now at Notre Dame. Sorry, Scott, I forgot to update. And this configuration is actually interesting because a lot of rotor stator configuration was tested. They could go from 14 to 28 stators. And also, you could basically move the distance between the rotor and the stator. So this configuration has been good, and also it was designed for noise localization and modal decomposition, so you have also upstream and downstream rings of sensors to do so. So it's an excellent test case for tonal noise because you have directivity, modal decomposition for several stator configurations. And on top of it, you have instrumented blades. So we can also compare the blade response. So our numerical ones, analytical one with the measurements. And I won't mention, but there is also some active control done on this configuration, but I won't show any comparison there. Now for broadband, we're using also another NASA test case, which is for the moment, I think, the only one actually that is open, which is the SDT, the Source Diagnostic Test Case. That was so it's a GE actually configuration. It's very similar to a CFM, I would say, 56 configuration in many ways, and it's a modern high bypass ratio. Which has like 22 rotor blades, and in its main configuration, so the reference one, 54 vanes, stator vanes. And this machine was tested in 3 configurations, but at approach, you have a full database, aerodynamic and acoustic database to compare with. So this is the one that actually I will be comparing with. And there are other configurations of stators, a low count one, and then a swept low count one. So low, this is called the low noise configuration. But as I mentioned, I will focus mostly on this one. So it's a unique broadband noise test case, and I suggest that everybody actually try it because it's quite interesting. Now, if I summarize everything I've shown so far in terms of analytical model, this is basically all the ingredients we have in our analytical broadband noise models. The needs for it are simple. We want to have fast-running prediction tools that are basically done in a couple of minutes now. And the same thing for transmission. It's based on strip theory to account for the flow in homogeneity, and it needs to account for cascade and even camber effects. We've done modifications that can also account for camber effect, basically. And this hybrid technique will have a 3D description of the excitation. We will include cascade effects when it's needed, and this is this rectilinear response, a 3D rectilinear response based on the Wiener-Haupt method. We corrected it also to account for the cylindrical dispersion because rectilinear is not the actual geometry. And then we can do either free field noise radiation or ducted noise radiation, so we can account for the duct or not. The free field one was proposed by Hansen, so that's Hansen model. And then for the ducted one, we have 2 models, one based on 2D response, which is Ventris model, and the 3D one, which is Poisson's model. So these are the results that we obtain on the SDT reference case. You see that, so on the top I'm showing, actually on the left I'm showing the acoustic power coming out of the inlet, and I'm showing on the right the acoustic power coming out of the exhaust. So inlet, outlet, and in these columns. And I'm showing 2 different things. So at the top, I'm comparing basically different, first, I'm comparing ducted, which is before going into the results, the black line in all these plots will always be the experiment, the NASA experiment, and all the curves, the other are like basically the models, so the analytical models. So first, if we focus on the red curve, will be the complete 3D model, ducted, and we compare to Hansen, which is in green, which is a free field. So there we can compare the effect of the duct. And you see that there are some differences, mainly downstream, and also for both cases at a low frequency. But otherwise, I think both are doing quite well and comparing quite well with the experiment. And this is the case for actually other flow conditions. Now, the second thing that we've compared at the top is all the other curves here correspond to isolated profile. So now we are comparing the effect of cascade with isolated profile. And you see that it's actually very significant. There's quite a big gap here, a little bit less downstream, but there is quite a big gap actually between the red line and all the other blue or purple lines. Now, a final thing that is compared, but this is, I would say, a little bit more complicated, but we can account also for what we call a supercritical or subcritical gust, depending on the, I would say, trace velocity. And we see that the subcritical gusts are really important only at low frequency. And this is very consistent with what we've seen in parallel on airfoil noise, so the very basic canonical problem of wall-bounded flows. So this is basically my top plots. Now at the bottom, I'm comparing two different things here. I'm comparing, if we start comparing the red and the blue, here I'm using basically two different blade response. I'm using the 2D blade response whereas with the blue line, whereas I'm using the 3D blade response with the red line. And you see here it's even more comparing and more different. Now we have a very different level between the two. So the 3D blade response is very a crucial step. The final thing that we are comparing, which is the green line, which is the original NANA-CME and NVIA calculation, using this 2D cascade response of interest. They used a different now turbulence spectrum for the impacting or impinging turbulence. They were using a Gaussian, basically, spectrum. And you see that between, so these two have the same blade response, but now the excitation is different. The turbulence spectrum is different. And you see that there is, again, a very big gap. So the impinging turbulence, to characterize it, is very crucial if you want to get something accurate. And I have to say that this was more help to fit the data than really, because the Lippmann spectrum that is used for the blue curve is more realistic, actually, than the Gaussian one. So if I summarize, that's a lot of information here. I want us to stress that it's very important to be 3D at all steps. So you need to have a 3D oblique gust, you need to have a 3D cascade response, and then you basically have something that is more realistic and much closer to the experiment and to the reality. And then at low frequency, you need to include a subcritical gust. And finally, the turbulence spectrum has to be very realistic and should be assessed either numerically or experimentally. And I will show actually an example on this precisely SDT case later on. Okay, the final thing that we have been looking at is the effect of swirl. Okay, I mentioned that we were assuming a uniform flow, uniform axial flow. Now, if you are in the interstage, so between the rotor and the outlet guiding vane, this is really wrong. You have a high swirl, and you're not accounting for it basically with your Green's function, analytical one. So we went to a modification basically of this Green's function. Now you are no longer analytical, unfortunately, because you have a sixth-order wave equation to solve when you have swirl. But if you do so, numerically you get your Green's function, then you can compare uniform axial flow with swirl plus shear flow. So this is my comparison now between, so the symbols are again my NASA data. The black line corresponds to my previous Poisson's model. The orange one is my new code, but putting swirl to 0, so this should correspond to the black one. So you see it's matching well, except in some resonance, but we can discuss that later on. And then we have the swirl effect. And you see that the swirl has actually some significant effect at low and mid frequency. So swirl is still, I think, a significant contributor here. Finally, the future effort will be to also include interstage liner, because I forgot to say it, but all what I've shown so far, we're assuming basically solid walls. So no effect of liners. We have done some effect of liner, but in a more simplistic case where we've done a propagation problem in a duct, where we basically include a lined section in a uniform duct, annular duct. And we looked at the effect of the swirl in this section as a function on the transmission loss, on the modal transmission loss, so transmission loss per azimuthal mode, by comparing basically the modal power transmitted with respect to the inlet power. Now, what we have seen from our analytical development, and if you want to have details, you can go to these two later GFM articles. The main effect, actually, of including swirl is basically to have this additional red term here in the Ingart-Meyer classical effective impedance. And you see that it's actually related now to your vortex design of your blade. So the swirl is playing this role. Now, from an acoustic point of view, swirls add a spin-like term in the mass spring damper system, original mass spring damper system that Inge and Meyer model describes. Now, these are the results, okay, at the bottom. This is a zoom close to 0. So this is the transmission loss, modal transmission loss of a function of the modal order, of the azimuthal order. The black line will be, in my case, without any swirl, so just uniform axial flow. And then I'm increasing basically the swirl. And I'm using one particular model here, but we did it for all kind of free vortex, force vortex, and so on. And there are some effects actually of swirl, and if you see, it's basically the whole diagram, which had this bell shape without swirl, is now actually rotating with respect to the mode of the 0. So what happened is basically you have a decrease here of the transmission loss for the co-rotating mode, and you have an increase of the transmission loss now for the contra-rotating modes. So swirl has basically this effect, increased attenuation of contra-rotating modes and decreased attenuation of co-rotating mode. And far from cutoff, I have to also insist. So this is basically one model. Now, one thing that is problematic in any of these models based on the strip theory is always you have rectilinear discontinuities between the different strips. And the other thing too also, because you have strips, you prevent basically any radial dispersion of the mode in the radial direction. So if you want to account for that, we've been developing now a new method, which is called the mode matching technique, where we basically now do a field expansion in orthogonal modes in each subdomain. So before a row, in the row, after the row. And if you do that, you can basically eliminate the need for basically having rectilinear response. And then what you do is matching the interfaces the acoustic field. So you ensure continuity of the acoustic field, so pressure and velocity at the different interfaces before and after the blades. So you end up with some infinite system of equations if you do so. So then you need to truncate, and then you just get the modal coefficients by matrix inversion of the truncated system. So the basic theory is not too complicated. It's quite involved actually to get it to work fine. But at least it eliminates this problem, basically, of the rectilinear discontinuities. So let's see some examples, and I will show 3 different examples. First, 2D examples. So far, we have been able to go actually to complete bifurcated waveguides, so complete channel with its actual dimensions. And I'm comparing here, I'm taking again my SDT test case with 54 stators. And I'm considering one strip at a Mach number of 0.4, and I'm considering the BPF of the machine, which is this 5,726 hertz. And for this particular BPF, you have 2 modes, 6 and minus 12, that are propagating. And we are looking at how basically the transmission is done through the rotor cascade. On the left, I'm showing some Euler simulation that were achieved with the bass high-order bass code by Hickson. And on the right, I will be showing the analytical model results. And I'm doing that for my two different modes. So if I look at the overall comparisons, I think the fields are very close, and we are really doing, you see, the same kind of qualitative results. Same thing here if you compare basically what's happening close to the cascade. When we look at the angles also of the waves that are basically either reflected or transmitted, we have also a very good match between the two calculations. And the other thing, the edge actually of the analytical model is that we don't have any spurious reflections from the boundary conditions that you see actually here and here in the Euler equation. So I would say, we have an excellent agreement with excellent results without the spurious reflection, basically. So this is 2D. Now, what do we do in 3D? So we did some 3D acoustic propagation, but here we did only flat plate. We did flat plate without any stagger angle or with stagger angle. And we were, this was a 2D example where we showed basically that if you don't have any stagger angle, basically you cannot produce any plane mode, and you have a symmetric, basically scattering. As soon as you introduce basically the stagger angle, you have a skewed distribution, and you now produce nicely the planar mode as expected. And then we went to also a 3D configuration to show that we could have this radial mode scattering that we couldn't have basically with the strip theory. And you see that we have a nice continuous field both upstream, so the blades are here, so both upstream and downstream of the cascade. And these are actually in good agreement with preliminary measurements that have been done in the LP3 setup at École Centrale de Lyon. Now, one case, so all of this was propagation. Now, one case of generation, and now we consider vorticity wave impacting, so turbulence interaction noise. And we consider basically a test case that is part of the EU project Ideal Vent. So we were considering this system, this stage. And we basically were able to both reproduce the modal content. The first blade passing, the first passing actually frequency was the third blade passing frequency, and we could get basically the good modal distribution and levels for the tonal noise. And more challenging was to see what we could get from the broadband side. And this is the measurements are in black here, so these are the measurements performed at VKI. And all the purple, pink, and green dashed lines are simulation. And actually, the purple one is a fully IDDS simulation of the system. And you see that we are doing actually as well. Our simulation is this cascade model here, and you see that we are predicting basically as well as this much more involved test case, and at a much lower cost. Of course, it's almost instantaneous compared to the other one. So the mode matching is, I think, another very promising method. Okay, enough of this analytical model. Let's move on to hybrid cases. All of this will involve numerical methods to predict the noise sources, and basically we will use different approaches depending if we want to get only tonal noise. So tonal noise is mostly generated by deterministic problems. So like mean wake impinging on the stator, for instance. And this can be really dealt with nicely with an unsteady URANS. And I will show some example of that. And it doesn't need turbulence modeling. Now, if you want to go to broadband noise, which cover all the frequencies, now you need to basically go to some more involved unsteady simulations where you have to resolve some of the turbulent eddies. So if you limit yourself to the larger eddies, you can do a large eddy simulation. And if you resolve all of them, then you can do a DNS. Now, for these two approaches, we have been using two different methods. One is based on the classical Navier-Stokes solving, and the other one is based on the lattice-Boltzmann. So on the lattice, we solve the Boltzmann equation, on the lattice. And this is my LBM here test case. Now, in terms of codes, we've been using mostly, I would say, CFX ANSYS for the unsteady runs, PowerFlow from Exa Dassault now for the LBM, and AVBP for the unstructured 3D LES compressible solver. Yeah, one thing I want to emphasize, all of these will be compressible simulations. So we are really solving also the acoustics in the field. And DNS is a little bit too costly, even though we start using it for airfoil noise. The first case we run was the compressor case, compressor wake interaction noise, because the blades are small and they don't need as much grid points. And also it's a low pressure one, research compressor, so we have a lower Reynolds number. And these are two examples. So we started doing the URANS and predicting tonal noise, and then we went to do some LES simulation that you see on the left. So what we learned from it is basically we didn't have any data for this one, any acoustical data, so we couldn't compare, but we did some assessment of some technological effects. And on tonal noise, we showed, actually with this thing, by changing the geometry here of the stator vanes, that viscosity, thickness, and camber had some effects, but the main one was really camber. We couldn't neglect viscosity and thickness, basically. So, and that's why we modified, actually, the analytical model to account for camber. Now, for what we learned from the LES side was the importance of actually the span-wise coherence length on the predictions. And this is also very consistent with airfoil noise. We know that the span-wise coherence of wall pressure fluctuations is one key element if you want to have a good prediction. So this is confirmed actually by the direct simulation here. Okay, giving some example of tonal noise prediction. And I will be using my ANCF test case. So this is the flow field in this machine. So on the left, you see by blade to blade isocontours of entropy, the flow topology from hub to tip. So at mid-span, everything is well behaved, thin wakes, nice interaction, no flow separation. And when you move to either the hub or the tip, you have this strong separation on stators, which are due to two nice corner vortices that you have both at the hub and at the tip. And you see the flow topology associated with it. And now if we look at the pressure fluctuation, this is the complete RMS, and this is the amplitude at the BPF. So you see that it's pretty concentrated at the leading edge, which is basically supporting the analytical model strongly, and we'll see that in the next slide. And you have some excess, actually, fluctuations due to these corner vortices. But one thing I want to emphasize is URANS is actually under-predicting the levels, and by a big margin, as we'll see in the next test case. And this is for all turbulence models, and we had a much better results with LBM using an LES approach, where we have much stronger, actually, levels. But I still haven't compared yet, so I need to do that. So precisely comparisons of pressure jumps. So moving from hub to tip for the first BPF, second BPF, and you see the experimental results in blue. The green ones are the URANS results. So you see that they are doing quite well at most places, except at the tip, at the 2 BPF, and this is due to the, I think, lack of pressure fluctuations in the URANS induced in the corner vortex, and the analytical prediction in red. And you see that the analytical prediction is actually matching quite well the URANS calculation, and consequently also the experiment. So differences are only seen, I would say, in the corner separation, and of course the analytical model cannot do much there. Now, what is the consequence? Because these are probably for aerodynamicists big differences, but what are the consequences on acoustic? And this is actually quite mellow. And we see here basically the prediction from both, again, CFD will be in green, red will be the analytical guys, and the black guy is the experiment. And you see that for both the BPF and the 2 BPF, we have a good modal distribution, and also we have pretty good, actually, levels for all different modes. Things start to be worse, actually, when you move to higher radial modes, which is, again, expected because of the strip theory preventing, actually, the scattering in the radial direction. So good overall, I would say, analytical and experimental agreement. Now, I will skip this one because this is basically the thing that is important here is we added actually a direct now simulation noise calculation with power flow, so the LBM. Now these are exactly the prediction on the grid, so we are not doing any propagating. So this is direct noise computation, and you see that we are doing quite well actually compared to the experiment, which is the white bar. And the other two are basically showing the effect of the camber modification, but I will skip this one. I just wanted to also show this one for tonal noise, which is a quite important result, which shows that The trend is not only we get the acoustic directivity quite well, so this is the sound pressure level measured around the machine, so for all these angles that you see here. And you see that we predict basically the directivity very well, like in the experiment. And on top of it, we get the trend in terms of here we're varying the rotor OGV, so the fan OGV distance, moving from 1 chord length to half a chord length, and we get the trend very well. Now you see also that the spectra are pretty well predicted. We don't have very big voxels on the blades in the wake, so that explains that the broadband noise is actually dropping beyond 1 kilohertz. But the tonal noise is quite well predicted. So if we refine actually the grid, we should probably get better results. Okay, from there on we also looked at heterogeneous stators distribution, and we did simulation, power flow simulation. We didn't have there any experimental result, but we compared the power flow result that you see at the top, and this is for one configuration here. We've done many more. And I wanted to show this slide because it shows the power of the analytical methods, basically. Because when you compare the sound power level now as a function of azimuthal modes, you can split basically in different components now with the analytical models, the different origins of the sound. So for example, for the homogeneous case, we could show nicely that everything was coming from the wake. So wake interaction, no surprise here. But the residual one that we had in the simulation, and also in the measurements in this case, were due to basically the distortion. We have a residual distortion at the inlet because of the experimental setup, and this is actually causing this level, this background level. So this distortion in wake. Now we add a small heterogeneous here, so we thicken one blade, stator blade, and we increase also its chord length. And now we look at the differences, and you see that basically now we have an increased background level. It's still wake dominated, but now we have a potential effect that is coming up and also popping up and contributing. So again, the analytical acoustic models really provide a nice idea of that. Finally, one thing that is important also with direct simulations is you can also discover like new mechanisms that had been seen actually in the 70s by Parker in some of Rolls-Royce machines, which are resonance. Okay, so we basically showed that in one configuration we had a beta mode, a beta Parker mode, and that was actually contributing to a tone that we didn't understand, that was not blade passing frequency at all. Okay. So this is really an interesting outcome of the unsteady LBM VLES case. And we showed also that it's a nonlinear interaction between the stator potential field and the rotor wakes. So I think it was a nice outcome. Now moving to broadband noise, and I will show only one case, which is basically the SDT case and the reference case at approach. So we performed AES simulation of a slightly modified version of it, because now we have 55 actually stators, just to limit the number of blades. But this is really the results that we obtain compared actually to the RANs. So in terms of overall performances, it's slightly worse actually than the RANs, because we probably are still missing grid resolution. But we are, I would say, nicely in the ballpark, and we are getting there. And we have very similar results as a parallel lattice Boltzmann method simulation. So far, there are two simulations, this LES and the LBM case. Okay, I will skip probably this one because I see that the time is actually flying. One thing I want to emphasize just from this blade-to-blade contours, one difference, and this is typical in all the simulations we've run when we compare basically the LES and the RANs, is we have actually thinner wakes with less deficit in the LES, which are matching actually closer the experiment than the RANs. And also we have flow detachment on the rotor in the RANs, which is not the case in the LES. And this is what happened now when you compare actually with hardwire measurements now at mid-chord. These are contours of mean velocity and RMS velocity at mid-distance between the rotor blade and the OGV. And you see, and these are hardwire measurements maps here, and you see that the RANs actually have this S shape of the wake, which is quite different actually than the hardwire measurement. And this is due to a flow separation, laminar flow separation in the RANs that you have actually with all models, because this has been computed now by many groups with different Turbulence model and different codes, and they all give that. Which doesn't appear in the LES. In the LES, you have intermittent flow separation and recirculation, but on the overall, on the mean, it doesn't appear. Okay, so it's too strong in the RANs, and you see that we recover basically the shape of the wake. Now, notice also that at approach, we have now a turbulent wake at the tip and a laminar one at the close to the hub and for half of the span. And this is seen also in the RMS components. Now, in the RMS component, we see that the LES are doing quite well, actually, compared to the hardware measurements for all three components. And this is what basically the results that we found. And the other outcome of that is that we have a quasi-local wave turbulence isotropy. And this is also very good news for the analytical model, because this is an assumption that you do also to be able to have an analytical prediction. Okay, this is aerodynamic, so I would say the overall aerodynamic field is pretty well predicted. What about the acoustic? So we did two acoustic prediction, one with a Fox-Wemps and Hawkins, and one with a Goldstein analogy, which is meant for annular duct. So in this case, we don't account for the duct. In this case, we account for the duct. First, the Fox-Wemps and Hawkins results. So my black line is the measurements, and all my colored ones are basically different cases. The red and the green correspond to Fox-Wemps and Hawkins based on the wall pressure fluctuations on both blades. And you see that we have the correct trend, but we overpredict the level. Now we did another one, which was a porous surface that was put actually at the interface between our stationary domain and rotating domain, where we had data, and we looked at actually the levels. And we are recovering actually now the levels much better, which show that basically things are behaving well. And then because of the grid resolution, we have a cutoff at 10 kilohertz. So overprediction of rotor contribution, and especially what is of concern is this guy, and we'll see that in the next, actually in the next plot. Then we went for Goldstein, so now we are comparing Fox-Wemps and Hawkins in blue here to the red, which is Goldstein accounting for the duct. Now, one thing that to be noticed is that my Goldstein now is recovering most of the levels, both the intake and the exhaust, so upstream and downstream, over a range which goes from, I would say, 3,000 hertz all the way to 40 kilohertz. And now we have a much also lower prediction even here. We still have this peak here, which is this, and we have it also here, which is, still comes, I think, from the low resolution in the tip gap. So this is what is being investigated now. On the left, I'm showing also some flow features. So it's totally laminar on the pressure side, and on the suction side, you see that it's turbulent at the tip and laminar more close to the hub. So, and I would say at the stage we can do a very good prediction with Goldstein. Now, final slide I show today is basically what the alternative, and this is some of the results that were achieved by Casalino et al. With the lattice Boltzmann method, so with power flow, and they basically simulated all the different flow conditions and all the different configuration with power flow. And what you see is basically now, so black is always black here, and blue is basically the experimental data, and these are their predictions. So you see that they are doing quite well up to a certain, and these are direct noise calculation, okay? These are not hybrid. And same thing, at cutback it's a little bit, probably not as good, but because it's cutting a little bit lower, but they can do it also even at high speed now. So I would say overall excellent agreement for all the cases they have run, and a good preliminary case where there are shocks. So the LBM is really coming up to speed. And I will skip this one. So we did some HP turbine noise also, but I will skip this one, and I will go directly to the conclusion. So I hope I have convinced you that we're able to do now some good analytical models for both tonal and broadband noise. And they can account for duct or not, and they can account for cascade or not. So Schwarzschild or Winhoff method. And then there is a nice alternative method being developed, which is the mode matching technique. And they are all efficient, accurate, pre-designed tools. And I showed only turbofan applications, but they can be applied to low-speed fans, propellers, compressors, all kinds of machines. And we've extended that to swirl and line walls. And again, there too, we should be able to extend the mode matching technique. These models are actually now included in a software platform that we call OptiSound. On the numerical side, I can say that the URANs are very efficient methods to obtain tonal noise. And what is coming up to speed and will be, I think, the current and future of this turbomachinery noise prediction is the ADS of these turbofans. Even though they remain unchanged, the first results are very promising. And then LBM, so lattice Boltzmann method, is also a very nice alternative on the numerical side. And it works also for high Mach number. Thank you for your attention.